Hello everyone and welcome to my channel. My name is Alessia and today we'll talk about the implementation and applications of Dijkstra's algorithm. Let's take this weighted graph and imagine that vertices represent cities, edges represent roads, and weights represent the travel time. In this case, we could ask ourselves, what's the shortest path from my current location to another point? Dijkstra's algorithm will solve our problem. Dijkstra's algorithm will find the minimum weight path from the start node to every node on the graph, and after that it'll be fairly easy to find the shortest path between the start node and another point. Let's take a look to the data structures we'll need during the development of the algorithm. We'll obviously need a graph with its vertices and edges. We'll also need two dictionaries. The first, path weight, maps from each vertex to the total weight of the shortest path. All values are initialized to infinity except for path weight of the start node, which is initialized to 0. The second, previous, maps from each vertex to the previous vertex in the current shortest path. Finally, we'll need a list to store the shortest path and a priority queue called remaining. The priority queue can be implemented with several data structures, like arrays, heaps, and others, but I'll implement it with a heap dictionary. It'll be a priority queue of all vertices of the graph, where each vertex's priority is defined by its path weight. I'll use vertices as keys and priorities as values, and thanks to this neat data structure, changing priorities will be easy and fast. Let's begin implementing the classes we'll need for Dijkstra's algorithm. First, let's write the vertex class. We'll need the initialization function and another function to add edges. Second, we'll need an edge class. It's not strictly necessary, but it makes the code clearer. Finally, let's write the graph class. We'll need the initialization function and another function to add vertices. Now, let's start the implementation of the algorithm initializing the data structures as we previously described. Let's go through all graph's vertices and set the path weight of all nodes but the start node to infinity. Next, let's set each vertex previous vertex to none, and let's initialize remaining with the initial path weight values. After that, we iterate through the vertices in remaining until it's empty, doing the following. We pop the vertex v with the lowest priority, meaning the one with the lowest path weight, and we check for each adjacent vertex if the path to it could be shorter than it is by passing through v. If that's the case, we update path weight remaining and set v as previous of the adjacent vertex processed. When remaining is empty, the path weight stores the weight of the current shortest path from the start node to each node. So, we can now reconstruct this path by tracing through previous. If we find a valid path, we return it. If not, we return path not found. Now, let's write a test class to check if our algorithm works correctly. In the first test, we'll build the graph from the initial example and then we'll check if the algorithm returns the correct path from B to D. In the second test, we'll build a smaller graph and then we'll try to obtain an invalid path, the one from H to I. Let's test it. Everything's okay. Let's now analyze the complexity of the algorithm through big O notation. We'll start with space complexity, excluding from our count the space needed to store the graph. As we saw before, for the development of the algorithm, we need 4 auxiliary data structures, 2 dictionaries, 1 priority queue, and a list. Every one of those has a complexity of O of V. Therefore, the space complexity of Dijkstra's algorithm is O of V. Let's now analyze the time complexity of the algorithm. Since we implemented the priority queue with a heap dict, the pop calls will each take O of log V time, as will inserting and updating entries. We will do one pop call for each vertex, so that's O of V log V. Additionally, on each edge, we might call one update operation, so that's O of E log V. Therefore, the total runtime is O of V plus E multiplied for log V. Let's now go through some of Dijkstra's algorithm applications. As you probably understood by now, Dijkstra's algorithm can be used in mapping services. Consider your city as a graph and represent every place with a vertex and the route between two places as an edge. Then, by using this algorithm, you can calculate the shortest route from one place to another. Dijkstra's algorithm can also be used for social networking applications. Many applications suggest the list of friends that a particular user may know. In this case, the standard Dijkstra algorithm can be applied together with other features, calculating the shortest path between users through the connections among them. Okay, that's all for today. Thank you for watching. The complete code is available on GitHub, and if you enjoyed the video and want to support me, like the video and subscribe. Ciao!